Let's talk now about the Xv6 address space. So the Xv6 address space is broken up. We have basically user mode is the first half of the address space, and then the kernel is reserved for the top half of the address space. So page tables are set up so that this is accessible in user mode and this is only accessible in kernel mode. And what do we have in the user mode? Well, the standard stuff. We have our user text and data at the beginning. We have the stack, and then we have a heap above that. The kernel mode includes the BIOS. So the BIOS was actually down at a low level in memory. What's up with that? What's actually happening, as we'll see in a moment, is that the physical memory is actually remapped starting at 8000 at the base of the kernel. Okay, so that comes up. And then what happens is we've got the code and the data for the kernel, along with then free memory, right? These are just the free physical pages. Let's take a look at this in a little more detail. So what do we have here? Well, we've got, again, the user mode is pretty straightforward. We've just got our code and our data. The stack is actually a single page. So we just have a 4096 byte stack right here. And so the stack is going to grow down, so it'll start here and move down. And then any dynamically allocated memory is here at the top of its address space. Over here on the right, we have the physical memory. So the physical memory goes from, well, it could go from 0 to 4 gigabyte, but we actually have a limit on how much memory Xv6 is going to support, and that's just shy of 2 gig. I'll show you the just shy in a moment. But the reason for 2 gig is that we're mapping this physical addresses into the top half of the virtual address space. Okay, so since this is only 31 bits that we can address, we can only handle 31 bits of physical memory. As we know, the physical memory space, we have this base memory up to 640K, and then a hole for I/O, and then we start the extended memory. So if you think about the fact that we load the kernel at the beginning of extended memory, then when we get mapped up into the top area of the virtual address space, that's why we have the kernel starting at kern base, which is that 8000 plus 100, basically 1 megabyte past kern base, which is this 1 megabyte right here. So we load the kernel here, that loads its text and data, and then we can start allocating memory, which is basically just the free memory, which is this extended memory that we've got here. Okay? If there's any extended memory past 2 gigabytes, then it's just unused. At the very top of the virtual address space is for devices. So we've got, I believe it's 16 megabytes of memory here at the very top. Sorry, not memory, address space, which is reserved for devices. So what that means is, so that maps to this top of the physical address space here, is this top area here. So that means actually the amount of physical memory you can use is slightly less than 2 gigabytes. It's 2 gigabytes minus this space for devices. Let's look in a little more detail at what happens to the user memory. So for the user, right, we're going from 0 to kern base. And again, kern base is just a 1 followed by 31 zeros. Okay, 8. 0, 0, 0, 0. We've got our code and we've got our data. And again, that's just loaded from the ELF file. And then we've got our stack, which, as I mentioned, is 1 page big. Okay? The stack actually has a guard page below it. We want to ensure that the program doesn't try to write over the stack. That is, go outside the bounds of the stack. If we put the stack right up against the data, then if we had, let's say, a recursive routine that had too many invocations, that would start writing data into the global data, and that would be no good. So we actually put a guard page, and we use the paging hardware to prevent writing in there by setting this to not be present. Okay, so that'll ensure that we'll get a page fault if the stack grows too big. What else do we have here? We have the heap, which of course makes sense. That's the entirety of the remainder of the address space. We also have on the stack, when we first start the process, we actually have to pass in argc and argv, right? A standard main. So how do we do that? Well, what we do is go ahead and let's kind of look at the top of the stack. So what's on there? So on the top of the stack, of course, we've got the return program counter. There is no place to return to, so we just put all Fs, right? A process should not actually return. It instead needs to exit when it's done. You might say, how does that work in C? Because you know we have a main program and we are always allowed to return from that. Well, the way that really works is what is called by the kernel is not main. It's actually another short piece of code in C that's part of the library. And what that does is call the real main. And if the real main returns, calls exit. So there's this little entry point whose job is just to call main. And if main itself doesn't exit, it will take the return result of main and do the exit for it. So we aren't going to be returning, so we have that FFFF. And then the first parameter is to main is argc, and the second is argv. So argc is pretty simple. That's just the number of arguments. Okay, let's say there are n arguments, and so this would be the value n. And then next, we have to have the address or an array of pointers to the arguments. So let's think about that a second. We need something like that. And if we have n arguments, each of these is itself a pointer. Right? Well, the question is, where are we going to keep that? If we kind of look here, we can't keep it in the text. We can't keep it in the globals because the process might not have made any space in there for the globals. We could possibly try and allocate memory in the heap, but really the way we do it is we put it on the stack. So we are going to have the array here on the stack, and we're going to actually have each string here on the stack true. So if this is, let's say, ls, and this is minus l, then we actually store the address of argument 0 we have. Well, one thing to note is this should really be argument 0, and this should be argument n. So let's look at this. So we have the address of argument 0. So that is basically this address right here. That is the address of argv0 is passed as a parameter. And what is argv0 plus 4? That is what's the next element in memory. It's argv1, argv2, all the way to argv at argc. So this contains all of the pointers in this array because we have argv0 and argv at 1 all the way to argv at n. So we have here, let's look, so this is a pointer to here. And this we can view as an array of n plus 1 elements. This one points up to here. And so we actually have argument 0, if this case is ls, it's going to be 3 byte. It's going to be an L, and then an S, and then a null character. So we will have basically something like this. We'll have on the stack a null, an S, and an L. That represents the first argument. So then if we look at the second parameter, It's going to be a null, an L, and a minus. Okay, so we want argv0 to point to here and argv1 to point to here. So now we want to put the actual pointers onto the stack. So we're going to go ahead and put argv1 on the stack, and argv1 is a pointer to here. So now effectively what we have is this is an array where this is argv0 and this is argv1. But the last thing we need to have on the stack is one more pointer that points to here. Because argv is an array that is the address. An array is the address of the first element of the array. So the address of the first element of the array is right here. So those are the values we're seeing in here. So that's how, there's this careful setup basically when you start a process to make sure we get the arguments correct. Again, those are just all stored on the stack. So what we know about processes on Xv6 are that they have their own page table, right? And in that page table, the initial part, the first half of the address space, is unique to that process. The second half of the address space is actually can be shared among all the processes, so they can share those page tables if necessary, because they're all doing the same mapping to that upper half of the 32-bit address space. And so each process is its own page table, and then the kernel will just change CR3 as necessary to switch which page table is active. Again, the address space is kind of, if we let's look pictorial. So if we have process 1 and process 2, and here we have the kernel, these pages would all be the same pages. And these pages are also set up in the page table such that they do not have the user bit set. So while we're in user mode, the process can only access the bottom half of the address space. It doesn't have any access to the top half of the address space, because if it tries to access any of these, it'll get a page fault because of the fact that the p bit is not set. However, the p bit is set in the lower half of the address space, and these will be separate mappings. And of course, this may be a sparse mapping because it's unlikely we're going to be using the entire full 2 GB address space. But if we haven't allocated in a heap, for instance, then we're going to just be using space for the code, data, and stack. And so there'd be a whole range of pages that wouldn't be allocated, and page table entries that wouldn't be present. Why do we do this sharing? Why do we even have any mapping of the kernel space with the user's page table? Right? Why is that mapping there? An alternate approach would be to just map the bottom address space, let's say, and then on a system call, as we enter the kernel, we could go ahead and change page tables and work from there. And the real advantage is it's kind of nice not to have changed page tables, right? So what this allows us to do is to go from user code into kernel code without changing any page tables. So that can be quicker and easier. And that also allows the kernel to read and write to the processes portion of the address space. Why would that be necessary? Well, for example, we want to, let's say, read and write parameters. So if we have a write call where we write a file descriptor and a pointer and a length, first off, where are these going to be stored? They're going to be stored on the stack, on the user stack. So we're going to need to, from our system call that is implementing write, we're going to need to read these parameters from the stack. Plus, for this pointer, that's going to be a pointer somewhere in this user space. And again, we're going to need to be able to read. So it's handy having this mapping already set up. That also means the kernel is mapped at the same location for all processes. That's also handy. That means whenever the kernel is running, it just knows that it's got this address space up here and everything is not moving around as it might be if we had somehow different page tables for different processes for the kernel. It's also easy with this setup for the kernel to read and write physical memory. So this provides an easy mechanism for the kernel to write to any particular physical address. So if it wants to write a physical address, let's say 1234, this is our physical address, it knows all it needs to do is add a high bit in front of that. So the corresponding virtual address is going to be 800 in hex 1234. So easy for it to convert back and forth and write to any location. The disadvantage, of course, is the fact that we are only allowing a maximum of 2 gigabytes of memory because all of our physical addresses we're requiring to fit in the top half of the address space. So that's basically how the X86 address space works, both how it works for the kernel, the mapping to physical addresses, and also how within a particular process we are actually dealing with the stack and the parameters to that process.